So we've seen edge operators which find edge points in images. These represent local intensity discontinuities. But we often want to find a boundary or curve in an image, for example, the silhouette of an object. And a boundary like this is composed of many edge points. So in object recognition, typically we want to, as a preliminary step, we want to reconstruct the boundary from local edge elements. And this may be difficult because, as you can see here, there may be a lot of edge points in the image which don't belong to the object of interest. So you may need a domain or object model to find which points belong to the curve you're interested in. So the technique you use to find a curve or boundary, it depends on how much knowledge you have about the shape that you're looking for. If we know the exact shape in 2 dimensions, then we can extract that complete contour. We can have methods that look for that exact shape. But another possibility is to just extract general, or if we have a general line or curve model, we can extract pieces of the boundary and then go ahead and link those together. If we don't even know that the boundary may be composed of curves or lines, then we can just try to connect a chain of edge elements together. And this is what the canny operator does, for example. The Hough transform is actually doing this. We're going to find line segments in the image from edge points. So the Hough transform is useful for finding lines, but actually any parametric curve. So for example, conics, ellipses, circles, parabolas, things like that. Anything that can be expressed in terms of parameters. The advantage of it, it's relatively unaffected by gaps and noise. It's very robust. And so basically, given a set of edge points, it finds the lines, one or more lines, which best explain the data. So let's see how that works. A line has 2 parameters. You can express it in terms of a slope and intercept, an m and a b, like this. So let's say we have an edge point located at x0, y0. So there are many possible lines that could pass through that point. In fact, all lines that satisfy the equation y0 equals m x0 plus b. So that would be this I guess, pencil of lines that pass through that. Or we can rewrite that equation in a different form, saying b equals minus x0m plus y0. So that's actually a line in the parameter space of m and b, where x0 and y0 are fixed. So if we have 2 points, if we have points on a line in image space, such as this, we have 2 points on this image line, they yield lines in parameter space, the space of m versus b. So all possible lines that pass through x1, y1 are shown in this blue line here in MB space. All possible lines that pass through x2, y2 are shown on this red line in MB space. So where those 2 lines intersect is the line that agrees with both of those, namely it's the line that passes through both of them. So the algorithm works like this. It has an accumulator array, which is a set of discrete bins for the values that we're looking for, namely m and b. So we decide what our minimum possible m could be, our maximum possible m, similarly for b here. So we initialize all those elements to 0. Then we scan through the image, and for each edge element that we find, we increment all the cells that satisfy this equation. So we know x, we know y, and we're finding all possible pairs of m and b. And every time we find one, we increment that cell. Then we look for peaks in this array, and those correspond to lines that pass through many edge points. So for example, this cell containing a 10 means that 10 edge points voted for that line. A problem occurs, though, with in that representation if you have vertical lines. In other words, you have an infinite slope. So m goes to infinity. To avoid that, we use this polar coordinate representation of a line. Rho equals x cos theta plus y sine theta, where rho is the vector from the origin to the perpendicular of the line. It's the perpendicular, closest distance to the line, that perpendicular distance. And theta is the angle from the positive x-axis toward the y-axis. So that avoids the problem with infinite slope, and it also allows us to use constant resolution for rho and theta. So now our parameter space is a rho and theta space, like this. And instead of a edge point generating a line in parameter space, it actually generates a sinusoidal curve like this. So the form of the curve is something cos theta plus something y theta equals rho. So let's go into a little more detail on the conventions we use. The angle for theta we're going to use from minus 90 to plus 89. So basically it ranges all the way down to here to all the way up to here. The value of rho we're going to choose as d max. So d max is the largest possible distance from the line. So in that case, that would be, for an image like this, a line passing through an edge point at the very far corner would have a rho that would be equal to this distance. So d max is essentially the diagonal of the image. So let's look at some examples here. So let's say we have a point at xy equals 50, 100. And let's look at some lines that pass through that. So one possible line is this vertical line, right? And that, the perpendicular distance here has an angle of 0 and a rho equal to the x value, which is just 50. Another possible line that could pass through this point is this horizontal line. In that case, the perpendicular has an angle of plus 90, and the distance, the length of that vector is 100, because it's just the y element. Another possible line is this diagonal line here, which would occur at an angle of 45 degrees. To figure out rho, let's go ahead and calculate that from the equation. So remember we had rho equals x cos theta plus y sine theta. So if I have an angle of 45, then cosine theta is square root of 2 over 2. So I'm going to have 50 square root of 2 over 2. And y is 100. And sine of 45 degrees is also square root of 2 over 2. So this is 150 square root of 2 over 2, or 75 times the square root of 2. And one more example, let's look at the case of a minus 45. In that case, we actually have a negative rho, because it's, instead of going up this way, the line is back behind us here like that. So let's calculate rho for that. So in that case, for a theta of minus 45, I'm going to have rho equals 50. Cosine of minus 45 is still square root of 2 over 2. Sine of minus 45 is minus square root of 2 over 2. So I get minus 100 square root of 2 over 2. Or minus 50 square root of 2 over 2, which is 25 square root of 2.